Hey everyone, and welcome to The Explainer. Today, we're unpacking some absolutely groundbreaking research from Brett Goodwin and the UAIS Research Group. This stuff feels like it's straight out of a sci-fi movie, but it is happening right now. We're going to look at how they've figured out a way to make autonomous drone swarms survive and actually thrive in totally hostile, completely disconnected environments. They've developed this incredible system called the FGSR framework, and it is a real game changer for how artificial intelligence operates out there at the extreme tactical edge. So think about a modern drone swarm for a second. Normally, these swarms are highly coordinated, super intelligent, and entirely reliant on massive cloud computing and a continuous communication link. But what happens when that swarm flies into a GPS-denied environment? Or what if it faces heavy electronic jamming? Well, for most standard multi-agent systems, the answer is pretty simple: catastrophic failure. The second you cut that constant network connection, the whole swarm essentially goes blind and deaf. Okay, let's dive into this. Because standard traditional swarms are surprisingly fragile. They basically assume they're always going to have a persistent network, constantly chattering back and forth, sharing state vectors and positional coordinates. You take away that central telemetry and boom, they suffer from massive single-point failures. In stark contrast, we have the FGSGR framework, which stands for Frequency-Governed Self-Graph Reasoning. It abandons that chatty architecture entirely. Instead, it relies on decentralized, edge-native compute. It creates this localized intelligence that gives the swarm genuine radio-silent resilience. Here is our roadmap for today. We're going to break this intimidating architecture down into 4 logical pieces. First, the GPS-denied drone problem. Second, tri-frequency perception and sync. Third, edge compute and surprise memory. And finally, the swarm immune system. Let's start right off with Section 1, the GPS-denied drone problem and the inherent vulnerability of the swarm. When a swarm gets deployed in, say, a tactical or industrial reconnaissance environment, things like electronic warfare jamming or, honestly, even just thick geographical shielding can completely collapse their network. Now, you might be wondering, well, why not just put a really smart AI on every single drone? The problem is, trying to run heavy, large language models or deep reinforcement learning models on tiny, weight-restricted hardware, like an NVIDIA Jetson Orin Nano, causes massive thermal and memory bottlenecks. Without those constant data feeds to keep them grounded, standard multi-agent systems suffer from what's called context rot. They literally just start guessing. And these purely probabilistic architectures suffer from catastrophic hallucinations, which in the real world physically means drones violently crashing into each other, blowing past flight boundaries, and just producing totally erratic behavior. Which brings us to Section 2, tri-frequency perception and sync, essentially the swarm senses. Now, what's really interesting about this slide is how the FGSGR framework solves sensory overload by acting almost exactly like a biological organism. A drone is constantly getting hit with tons of multi-scale signals: propeller vibrations, optical flow, long-range tracking. Standard systems try to process all of this in uniform frames, which either wastes precious compute power on really slow trends or completely misses sudden micro-anomalies. But FGSGR uses spectral CAN networks to split data into 3 isolated operational bands. You've got the high band, running at 12 Hz or more, which acts like unconscious reflexes, handling sudden wind shear and dodging immediate obstacles. Then the mid-band, at around 5 Hz, acting as conscious thought for trajectories and routing. And finally, the low band, taking at about 2 Hz, which serves as long-term memory for things like environmental drift and global mission tracking. So how on earth do they coordinate if they absolutely cannot use their radios? This is where a concept called coupled oscillator dynamics comes into play. It's a system where independent, rhythmic agents implicitly synchronize their internal timing loops just by observing the physical behavior of the agents around them. Think of it exactly like fireflies flashing in unison in a dark forest. It's beautiful, right? These drones use implicit sync. They visually track the flight cadences and physical intervals of the units nearby and use that to align their internal loops asynchronously. If a drone suddenly needs to make a crazy, evasive maneuver, latency capping overrides force the slower memory loops to pause, so that high-frequency reflex processor never starves for compute. The result? They stay perfectly synchronized and absolute radio silence, completely avoiding enemy electronic detection. Okay, moving on to Section 3, edge compute and surprise memory. Let's talk about the swarm's brain. Trying to store historical context on a tiny edge device is a nightmare. It normally causes a quadratic memory explosion. You can't just record hours of 30 frames per second dense video telemetry. So the framework uses something called dynamic Bayesian surprise gating. It's continuously calculating the Kullback-Leibler divergence, which is basically just a mathematical measure of surprise between what the drone expects to happen and what is actually happening. So instead of remembering every single detail, the drone only commits to memory when it experiences an unexpected physical or informational transition, like, say, suddenly entering a new corridor or spotting a hidden object. When that surprise metric spikes, it compresses the moment into a lightweight symbolic graph. It literally only remembers what matters. And this brilliantly illustrates how the drone makes fast, tactical decisions when faced with an ambiguous scenario, using a generative recursive reasoning model, or GRAM. Step 1, the outer loop captures the global flight context. Step 2, the inner loop branches out parallel path hypotheses by injecting stochastic perturbations. So it's basically instantly brainstorming a bunch of different routes. And then step 3, a local Q-head using a probabilistic tiny recursive model, or PTRM, verifies the logical consistency of those paths to preview optimal navigation. And it does all of this in milliseconds. You can think of the PTRM as a localized imagination engine. It injects a diminishing layer of Gaussian noise at each recursion step, which smoothly evolves the drone's internal state vector. This is huge because it allows the drone to navigate complex solution basins and escape local minima. It's mutating and refining its own ideas entirely within the VRAM of a tiny edge device, maximizing its deduction accuracy without needing a single expensive external API call to a cloud server. Let's move to Section 4 and see how this all builds up to the climax of the tech, the swarm immune system and neurosymbolic governance. The single greatest threat to any decentralized swarm is data corruption. If even one drone gets its sensors blinded, gets physically damaged, or gets hacked, it can spread that corrupted data and take down the entire swarm. FGSGR stops this cold using a lattice deduction transformer, or LDT. It projects every state onto a mathematical lattice, calculating the infimum, which is the greatest lower bound, and the supremum, the least upper bound. Think of these bounds as strict, immutable physical and logical laws, things like maximum flight envelope limitations or absolute structural integrity margins. So the crucial point is this exact fail-safe decision tree right here. Before any movement is ever executed, the system calculates those infimum and supremum boundaries. It then verifies that the drone's invariant context anchor rests strictly inside them. If those bounds are violated for any reason, meaning the drone is either hallucinating or damaged, the validity mask instantly drops to 0.0. It doesn't guess. It executes what they call explicit abstention. It freezes the state transaction and safely falls back to historical memory or triggers an automatic braking routine. As Brett Goodwin himself notes in the research, this isolates compromised elements completely at the single agent level, preventing the propagation of corrupted data across the wider swarm architecture. What that means in practice is it creates a self-cleansing swarm. If a drone starts acting anomalous, it instantly quarantines itself. It just silently drops out of the coordination loop to save the collective. And to prove this wasn't just theoretical math, the team put it through an automated edge validation test suite, actively injecting adversarial corruption. The results? FGSGR achieved 100% batch-level isolation. Absolutely flawless. The mathematical trace from their experimental harness proved it perfectly. When they injected a heavily corrupted state into batch index 0, the LDT validity mask dropped symmetrically to exactly 0.0, forcing that local lattice abstention. But meanwhile, batch index 1, sitting right next to it and operating with valid input, successfully processed and updated its trajectory without a single drop in performance. This guarantees completely deterministic fault isolation directly inside continuous latent spaces, totally removing the risk of those dreaded cascading failures. So by replacing massive cloud dependencies with multi-scale spectral pipelines, surprise-driven memory, and absolute uncompromising neurosymbolic guardrails, the FGSGR framework brilliantly bridges the gap between high-level logical reasoning and real-time physical control. It is just an incredibly elegant solution to one of the hardest problems in robotics today. Which leaves us with a pretty thrilling question to ponder. With decentralized, biology-inspired swarms now mastering the edge in complete silence, what limits actually remain for hardware-in-the-loop autonomous intelligence? Thank you so much for joining me for this explainer, and definitely keep your eyes on the skies.